All right, as a follow-up to our previous video where we solved a system of linear equations using an inverse, I want to talk about what's going to happen when A is not invertible. So let's let A be the matrix 4, 1, 8, 2, and X will be X1, X2, and B is going to be the matrix, let's say 4, 3. So what I want to do is I want to think about solving the system, and let's think about what's going to happen. So, all right, we can do this a few ways. One, the first thing that I'm going to point out is that A inverse does not exist for this example, because what's the determinant? The determinant is going to be 4 times 2 minus 8 times 1, which is 0. So that means that A does not have an inverse, and therefore the previous method can't work. But maybe there's still a solution, maybe there's not. We just have to figure out, are there 0 solutions or infinitely many? We've ruled out that there can't be a unique solution. Okay, so we know that if A has an inverse, then there's a unique solution. So if A does not have an inverse, there's not a unique solution. It turns out that that's also true. So what we're going to do then is we can solve this doing just kind of the same old stuff that we did. You can, however you want to do it is fine. Let's just do augmented matrices. So we're going to solve, and we'll write this as an augmented matrix. We take our coefficient matrix, augment it with the constant matrix, and then go to town and simplify. So one thing that you can do, just if you can see right away, is that we can add, we can replace, I need a little bit more room here, row 2 with row 2 minus 2 row 1. And if we do that, row 1 will stay the same. We're going to end up with 0, 0, negative 2. And so let's think about what that means in terms of a system of equations. If we think about it, this has no solution. The reason is that this bottom row says that 0x, so this bottom row here, says that 0x1 plus 0x2 equals negative 2. Doesn't matter what else is going on, there's no solution to that equation. There's no values of x1 and x2 that'll make that true. So that means that the system has no solution and we can stop. Okay. On the other hand, let's think about if we have ax equals b, where a is going to be 1, 1, 3, 3. X is going to be our variable matrix just like before, and B is going to be, let's see, we could have, let's say 4, 12. Okay, so let's check at what's going to happen here. And if we were to do this, again, the determinant is 0. You can just check that the determinant is 0, so A inverse does not exist. So we can't just find the inverse, multiply on both sides by the inverse and solve. We just have to do this the old way. So we're going to look at the augmented matrix. We have 1, 1, 3, 3 augmented with 4, 12. And so if we were to simplify this, let's say we take row 2, subtract from it 3 row 1, we would end up with, so the top row will be the same, 1, 1, 4, and we would end up with 0, 0, 0. And now the bottom equation, even though there's a 0, 0, the right side is also 0. So we can stop. There's no more simplifying that we can do here. This is in reduced row echelon form. So our solution, our set is going to be, our solution set is going to be all the pairs of numbers x1 and x2 satisfying x1 plus x2 is equal to 4. And if you'd like, you can parameterize the solution. So you can parameterize in terms, what I mean by that is write your solution in terms of a common parameter, say t. Let's say x2 is t, and then x1 has to be 4 minus x2, or 4 minus t. So your solution is going to be all the values x, where x is equal to 4 minus t comma t for any value t, for any real number t. Okay, so for any real number t. So that's going to be your solution there. Okay, so it turns out in this case there's infinitely many solutions. So let's summarize what's happened here. Let's summarize. If A inverse, my pen has stopped working here. If A inverse exists, then AX equals B has a unique solution. And if A inverse does not exist, then AX equals B has either, there's only two possibilities. It has either 0 or infinitely many solutions. But we know that there's not one solution. So if A inverse does not exist, then we no longer have a unique solution. Either there's no solutions or there's infinitely many. And let's think about what this tells us about this system. So let's consider AX equals 0, where A is some matrix. I don't care what it is. Let's just make it a generic matrix, A, B, C, D. X is our variable matrix. And here by 0, I mean 0 is the 0 matrix. This is the 2 by 1 0 matrix, 0, 0. And now when I think about what's going to happen, we know that, so I really just want to apply what we just said to this situation. We know that if the determinant of A is not 0, then A inverse exists, and that means that AX equals 0 has a unique solution. What is that unique solution? Well, X is A inverse times 0. And it turns out that if you multiply by the 0 matrix, as long as everything is defined, you end up with 0. In this case, it's the 0 vector. A and therefore A inverse are 2 by 2 matrices. 2 by 2. The 0 vector is a 2 by 1 matrix, so you end up again with a 2 by 1 0 vector, or the 2 by 1 0 matrix. So it turns out that there's a unique solution, and it's X equals 0. On the other hand, if the determinant of A is 0, then A inverse doesn't exist, and we have to go back to thinking about how to do this in general. So I want you to think very carefully what would happen if the determinant of A is 0, and therefore A inverse does not exist. Okay, in fact, I would encourage you to pause at this point and think about what is this going to say about the system AX equals 0. So hopefully you paused and thought about this for a second. But we know that if A inverse does not exist, then the solution, the system, or the matrix equation, however you want to think about it, has either 0 solutions or infinitely many solutions. If you have AX equals 0, it turns out that you always have at least one solution. You can always take X to be the 0 vector of whatever appropriate size, and then you'll have that solution. So there's always at least one solution, namely when you have 0 all the way down. And if the only possibilities are that you have 0 solutions or infinitely many, and you already know that you have at least one solution, well, the only thing that you can conclude is that AX equals 0 has infinitely many solutions. It can't be that you have no solutions, because you already know that there's at least one. namely the zero vector. So it must be that Ax equals 0 has infinitely many solutions. Okay, and again, we get this all from thinking about what's the determinant of A. Okay, so if we know the determinant of A, then that tells us what's going to happen to our system of linear equations.